RF Man here. Today I'm going to continue my discussion on how to design, build, and test an RF amplifier. But before I get into part 4, I had a couple of questions from some viewers. So one viewer asked me, do you have to have the bias voltage applied to the transistors in order to get an accurate measurement of the SWRs? And the answer is yes. I can simply shut off the power supply, and you can see the bias voltage here is at 0, and you see there is a significant increase in the SWRs, both on the low end and the high end. And of course, if I restore the power, now we see a 4.2 volt bias, and we see the SWRs return back to where they originally were. So yes, the bias voltage needs to be applied, and preferably the bias voltage that you'll be using in your application. The second question I had was, could I get a lower response on the lower end of the band if I add a trimmer capacitor? So if I use the trimmer, can I lower the SWRs on the low side? So I modeled this in Spice. I didn't see much of an improvement, but I'm going to go ahead and just adjust the trimmer capacitor real time, and we'll see the effects. So right now, the trimmer is set to about 5 picofarads. That's as low as it'll go. And there we turn it up. It's 1.64 on the low end. Okay, so we'll give it another full turn. 1.65, I don't see any improvement. Let's go ahead and adjust it a little more. Now I actually see it rising on the low end of the band and the high end. So the trimmer really doesn't help us much. We're better off using the dampening resistors in this case. I would encourage everyone to try a trimmer capacitor, see if it does help you. Remember, every board's going to be different. Every transformer is going to be different. We've got parasitic capacitance and parasitic inductance and component variation. So I would encourage anyone that's working on an amplifier like this to try to trim the input transformer as well as the output transformer. So that's a quick demonstration. Now I want to move over to our discussion, and this will conclude what we plan to cover in part 4, which would be the input board. So if I zoom in on this a little bit, this is the specification for the IRF510. And let's just go through some of the important parameters. The devices are rated for 100 volts. Okay, that's the drain to source breakdown voltage. So typically we want to operate below that, so we have some design margin. Typically 50% derating would be preferred. Actually, when we look at the LTSpice technology, like a BLF 188, it's rated for 135 volts. That's the breakdown voltage, but we operated at 50 volts to give us some good design margin. So I wouldn't go above 50 volts here. 50% derating is pretty standard in the development world. And the continuous drain current is 5.6 amps. Okay, and power dissipation per device would be 43 watts. Okay, so 2 devices, 86. Okay, and now if we take a look at the gate threshold voltage, okay, and this is the symbol here, VGSTH for threshold. Okay, it says minimum 2 volts, maximum 4 volts. I can tell you with the recent orders that I received, they're all at about 4 volts. They start conducting at about 4.1 volts. I have not seen any in years that were down in the 2-volt range. But it's always good to test the devices and test each lot and see where that actual threshold is. And of course, you're going to get lot-to-lot variation. So this one that I'm using, this pair is 4 volts and starts to conduct when we go slightly above 4 volts. So those are the important parameters on the data sheet. Of course, there are others, but for our discussion, that's adequate. Okay, so what we demonstrated in part 3 was how to set the bias voltage. And of course, increasing the bias voltage increases the drain current. So at 4.2 volts, we're basically at the quiescent point where we just start to conduct drain current, just start to turn the transistor on, and we typically say that's AB biased. So this is the conduction angle, okay, and the conduction angle is nothing more than the amount of degrees that the transistor turns on, okay, and there's always a trade-off here, okay, between conduction angle and efficiency and conduction angle and linearity. So if we start at the left, class A, transistor's fully on, fully conducting, it's less efficient, but it has a very high linearity, right? We capture the whole 360 degrees of the sine wave, okay? We go to class B, right? Well, we've got basically a lower linearity, but a higher efficiency because now the transistor is turned on only half the time, 180 degrees. Okay, so class AB is a compromise, right? We get pretty good linearity, little lower efficiency, and like everything else, engineering is a trade-off, right? And we see the conduction angle is between 180 and 360, so we'll call it 270. And that's where we try to bias this. Again, that's usually the quiescent point. For a bipolar transistor, yeah, you would do the same thing. It's usually around 0.6 to 0.7 volts, and you start to see current flowing through the collector, and you'd bias it that way. Remember the difference, LDMOS transistors, MOSFET transistors, the whole family of MOSFETs are voltage devices. So the amount of actual gate current is extremely low. It's milliamps at that. However, with a bipolar transistor, yes, you can bias those with quite a bit of current. Okay, so we're operating in class AB. Now, when we bias it, let me reposition my camera here again. When we bias it, we see the threshold is 4 volts, okay? I start to turn on about 4.2. That gives me 300 milliamps of drain current, okay? So we're at class AB, okay? And then when we drive it, we want to stay in the linear region or the active region here, okay? So between the active region, okay, if we drive it too hard, we'll saturate the transistor. And if we drive it too low, we're just going to cut it off, right? It'll be switched off, okay? So we want to bias it in between so it stays in the active region. And you can see if it's too high and it goes into saturation, we clip it off. And if it's too low and it goes into cutoff, we also clip it off. So we want to bias it so it stays in the active region. That's a very important point. And you can check the waveforms with an oscilloscope to see exactly where you're at. It's pretty easy to increase the drive and actually watch the sine wave clip off on the scope. Okay, so we said we were going to use LTSpice to measure the input impedance of the circuit and then actually simulate the entire circuit as well. So what I have here is how we calculate the coupling coefficient. So here's our transformer in the circuit, And we already said we're using a 1-to-1 ratio, so the primary and secondary each measure 11.2 microhenries, okay? And we're using material 43. The same is true on the output transformer. And we already went through the procedure of doing the open short test to calculate the leakage inductance. So we found the leakage inductance was 33 nanohenries. So this is the formula here to calculate the coupling coefficient. I take the square root of 1 minus what the inductance was when it was shorted and what the inductance was when it was open, okay? And that's a primary inductive, like I said, when the secondary is open, primary inductance when the secondary is closed. So here's the open measurement, 11.2, which is what we'd expect. And then here's when we short it, okay? It's 0.033 microhenries. So if we go 1 minus 0.0033 microhenries divided by 11.2 microhenries, and then we take the square root, here is the K value, 0.9985, okay? And that's basically 99.85%. So that's what we'll use for the input transformer, and we'll do the same thing for the output transformer as well. And we'll calculate what that K value is, or what the coupling coefficient is for the transformer, and we'll enter that into the simulation and then make our impedance measurements. So that's what we're going to do next. We'll go back to LTSpice and take a look on how we measure the impedance. All right, so now we're going to take a look at the circuit in LTSpice. This should be familiar to you. This is the original schematic that I showed in part 1. And this is the Spice model. So a couple of things we can do here. We can run the circuit and check the power output, see if it correlates with the actual prototype. And then I'm going to focus on the input side of the circuit for now and show how we measure the input impedance. So if we do a right click and we say edit simulation command, okay, first thing we want to do is run a transient analysis. So we have to enter in 3 parameters: our stop time, which we'll put as 60 microseconds, and our start time, we'll delay that by 10 microseconds. Let me just correct that. And then number of steps, we'll just go 1 nanosecond and click OK. Now we can go ahead and run the simulation. And one thing that I want to look at is the output power. So what you do is you can mouse over the load resistor, okay, and then press Alt, and you see that little temperature icon comes up, and then click that, and it'll show us the output power and the corresponding waveform. So that's what we would expect to see, a sine wave, and we see that it's about 50 watts or so. And when we demonstrate the prototype, that's basically what you'll see on the watt meter on the power output. So we're outputting about 50 watts, so the circuit's running properly. So we can close that simulation. And now we want to go back and edit the simulation command. And this time, to measure the input impedance, we're going to do an AC analysis. So here we have to enter in the type of sweep. This is basically the scale. So we're going to make the scale linear. And the number of points, we'll enter 10. That gives us pretty good resolution. And then the start frequency, we're going to use 10 meg, which is 10 megahertz. And the stop frequency we're going to enter as 30 megahertz. You can enter MEG or MHZ and click OK. Now, we're going to run the simulation. And let me just zoom in on the input circuit so you'll be able to see that a little clearer. Okay, and I reviewed this in part 2, pretty much the same procedure. So what we need to do is we mouse over this trace, and that's our voltage probe. Okay, so if we want to see the voltage from the AC source, in this case, it's an AC generator, but it could be a transceiver as well, any 50 ohm source. And we will go ahead and click, and there's our voltage. Now, remember what we said, that impedance, which is basically for DC resistance, okay, we can apply Ohm's law. So E divided by I, okay, and here we have to specify the current through L1, looking at the input side of the transformer. So we measure the current through L1, so we put that in parentheses, okay? And this just tells us Z equals E over I, right? Same as DC, R equals E over I. Okay, we click OK. All right, and then we have to mouse over to this scale on the left side. You'll see the little ruler come up. And we do a right click. And we have to change the plot from a Bode plot to a Cartesian plot. I explained what a Cartesian plot was in part 2, if you're interested. But basically, it allows us to plot 2 different parameters at the same time. Okay, and then click OK. And there we see our input impedance. So on the left side of the scale, we have the real part, which is resistance. And on the right side of the scale, we have the imaginary part, okay, which looks primarily capacitive because you see the negative signs there. So if you click on the center of the screen here, there's a cursor, and we can take a look at the impedances at any of the frequencies. So let's start with the center frequency, right? We're scanning from 10 megahertz to 30 megahertz, 20 megahertz bandwidth. We'll start in the center of the frequency, 20 megahertz, and I have real part 47.7, imaginary part 12.2. Now remember what we said, we take the square root of the sum of the squares. So I've already done that here on the spreadsheet. Here's 20 megahertz, here's our 47.7 real part, we square that. Here's the imaginary part, we square that, we add them together, we take the square root, and it's 49.26 ohms. And when we calculate the SWRs, which just is a ratio of the source resistance and load resistance, we see the SWR as 1. Okay, so let's go back to LTSpice now. Let's take a look at 10 megahertz. So we have 56.5. Let me just bring this up here so you can see where I'm reading. Okay, so here's the cursor position. As I move the cursor, you see the numbers changing there. So I'm going to go all the way over. Okay, there's my 10 megahertz. And here's the real part, 56.5. Here's the imaginary part, minus 5.5. And again, if we go to the spreadsheet, and we have 56.4 and 5.4. Okay, that was from my measurements a little earlier. Okay, we see that we take the square root of the sum of the squares, and we've got basically 56.7 ohms, let's call it. So when we calculate the SWRs, that's 1.1. And then if we go to the other side, to 30 megahertz, okay, you can see we have 39.8 and 12.1. So back to the spreadsheet, 39.8, 12.1, square root of the sum of the squares. We've got about 42 ohms. That's a 1.2 2 SWR. So you can see that we have pretty good SWRs all the way across the 20 megahertz bandwidth. So now let's take a look at the circuit and say, okay, I'm using a 1-to-1 here, so it allows me to measure the actual impedance of this circuit because this is 1-to-1, and I demonstrated that in part 2. Okay, but let's say using the 1-to-1 transformer, okay, instead of measuring very close to 50 ohms, let's say it only measured 25 ohms. Okay, what would that tell us? Well, if it measured 25 ohms, then my ratio would have to be 2-to-1. So I'd have to change the 11.2 to 22.4. That would give me a 2-to-1 ratio. So that would be 2 more windings. Okay, it would give me the 2-to-1 ratio. And then I'd be able to transform the 25 ohms that I measured with the 1-to-1 ratio would then be transformed from 25 ohms to 50 ohms. So using a 1-to-1 ratio to begin with actually allows you to measure the input impedance of the circuit. Now with this circuit, it happened to be very close to 50 ohms, and the 1-to-1 ratio is the closest that's available in this type of transformer. So I kept it 1-to-1. But again, if this was 1-to-1, and instead of measuring close to 50 ohms, I measured 25 ohms, I would just go with a 2-to-1 ratio. And then when I measure the impedance, okay, even though this measured 25, with the 1-to-1 ratio, if I change it 2-to-1, I'll actually measure 50, okay, because I'm transforming the impedance by the ratio of the input transformer. So I hope that's clear. That's why I typically start with a 1-to-1 ratio with any circuit, and then I can use that to determine what the proper ratio is after I have the impedance measurement. So I hope that was clear, and this will basically be demonstrated again when we do the bench testing. We'll be able to look at the actual performance and see how well it correlates. Okay, RF Man, thank you.